Now in this lesson, we are going to start our discussion on nuclear physics. Who gave us the concept of nucleus? Who told us that an atom has got a nucleus at the center? Rutherford. He gave us the concept of nucleus. Remember that famous gold foil experiment? Based on that, the concept of nucleus came. When we are studying the nucleus, we call them nucleides. Nucleides are nothing but nucleus. Okay, nucleide is a nucleus. So when studying the nucleus, we call them nucleides. Inside the nucleus, we have got protons and neutrons. These protons and neutrons, they stay inside the nucleus. They are called nucleons. So the particles that stay inside the nucleus, protons and neutrons, are called nucleons. Every nucleus will have an atomic number. Atomic number is written as Z. What is the other name for atomic number? Proton number, right? Protons stay in the nucleus. The number of protons is the atomic number. So Z is the symbol for atomic number or proton number. Every nucleus has got some number of neutrons, and that number we denote as N, that is called neutron number. The sum of these two is known as mass number. Mass number is written as A, and that is nothing but Z plus N. Elements with the same Z are called isotopes. Elements the same N are called isotones. This N should remind you of this N. Don't get confused. Isotones, same N. And same A, they are called isobars. Now, out of 1500 known nucleides, less than 260 are stable. Rest are radioactive. Those are known as radionuclides. Radionuclides undergo decay or disintegration by emitting a particle and thereby transforming to a different nuclide. If you think of one element, gold. Gold, what is the symbol? Au. Gold atomic number is 79. This gold has got 32 isotopes, out of which only gold 197. Mass number we write at the top, okay, either this side or that side, and atomic number at the bottom. So gold 197 is stable, rest are radioactive. Now, if you look at the periodic table, there is only one box for gold. So various isotopes of gold we cannot put in separate boxes and write their properties. For that, we have got something called nuclidic chart. In a nuclidic chart, either Z or N will be on the y-axis, so let us take Z here, and N is on the x-axis. So gold, all isotopes will come in separate boxes here. Here you can write down gold 197, which is stable. Right? Here we will get gold 198, which will be radioactive, so we can write its half-life. Half-life we'll learn a little bit later. Gold 196, gold 195. So you can write their properties, their half-lives, whether they're stable or radioactive in this nucleic chart. Radioactivity was discovered in 1896 by Henry Becquerel. Now, which nuclei is stable? Which is radioactive? For that we have got this kind of graph again. We can have Z on the y-axis, N on the x-axis. Okay, some people may do it the other way around, makes no difference. This is a line at 45 degrees. That means along this line everywhere N is equal to Z. For light nuclei up to calcium 40, we will find that N is approximately equal to Z for stability. Look at light nucleides, number of protons and number of neutrons are almost same. This happens up to calcium 40. Now as we move to heavier nuclei, for stability, typically there are more number of neutrons compared to protons. So this graph bends like this. This is line of stability. Any nuclei close to this line will be stable. Anything far away from this line will try to come closer to this line by emitting some particle, and that's radioactivity. So nuclei here may try to come here, a nuclei here may try to come here. The heaviest stable nuclei is bismuth. Bismuth 209. Bismuth atomic number is 83. So how many protons it has got? Number of protons will be 83, the atomic number. What is the number of neutrons? This will be equal to 209 minus 83. That gives you 126. So the number of neutrons is more than the number of protons. By how much? 43. That's quite huge. You see, in heavy nucleides, the number of neutrons is more than the number of protons. You can think that in a heavy nuclei, too many protons are there. There is some repulsive force, strong repulsive force, electrostatic repulsive force. To compensate that, there are extra neutrons. Too many neutrons also make the nuclei radioactive. So we need protons, we need neutrons in a particular ratio to make it stable. Now, the heaviest stable nuclide is bismuth, mass number 209, atomic number 83. Anything heavier than this will always be radioactive. Up to calcium 40, number of protons are almost equal to number of neutrons for stability, and this is what is called line of stability. Near this line, if a nuclide is here, it will be stable. Far away from this line, it will be radioactive. Radioactive disintegration will always try to bring nuclei closer to the line of stability. In this lesson, we are going to learn about radioactivity. Radioactivity is of two types, natural and artificial. Some naturally occurring nucleides are radioactive. Some nucleides we make in the lab, they are radioactive. So radioactivity is of two types, natural and artificial. In radioactivity, the first nucleus or the first nuclide that undergoes radioactivity is called parent nucleus. This parent nucleus will decay or disintegrate to give us daughter nucleides. Daughter nucleides will decay and give us granddaughter nucleides. In radioactivity, you don't get any son or grandson. You get daughter, granddaughter nucleides. Now, this is the line of stability. This is Z, this is N. This line is at 45 degrees up to calcium 40, and then it bends towards the neutron axis. Okay, the number of neutrons. Anything that is radioactive will always try to move closer to the line of stability. That is the first most important property of radioactivity. Radioactive disintegration tends to produce nuclei closer to the line of stability. A nuclide here will come here, never try to go far away. A nuclide here will come this side, always closer to the line of stability. Second property of radioactivity. Radioactivity is a nuclear property. Alpha particles, beta particles, and gamma rays are all emitted from the nucleus. So remember this. Don't think that these beta particles, electrons, so they are coming out from outside the nucleus. Every particle, alpha particle, beta particle, and gamma rays all come out from the nucleus. Third important property of radioactivity. This radioactivity involves huge amount of energy. Hence, it is not affected by external temperature and pressure. Next property of radioactivity. A particular nucleus at one time will either emit an alpha particle or beta particle, not both together. From one nucleus, you cannot have alpha particle coming out and beta particle coming out at the same time. Either emit an alpha particle or a beta particle. Gamma rays are emitted with both alpha particles and beta particles. Now, some nucleides are there which can decay either by alpha decay or by beta decay, but this alpha and beta will not come out from the same nucleus at the same time. Some nucleides decay only by alpha decay. If you look at uranium 235 or that for that matter uranium 238, they always decay by alpha decay. There is no way they can decay by beta decay. If you look at carbon 14, it always decays by beta decay, never by alpha decay. But if you look at actinium 227, this can decay by either alpha decay or beta decay. But a particular nucleus at one time will either emit alpha particle or beta particle, not both together. So these are the properties of radioactivity. First of all, radioactive disintegration will always tend to produce nuclei closer to the line of stability. Next thing, radioactivity is a nuclear property. Alpha particles, beta particles, gamma rays are all emitted from the nucleus. Third property, radioactivity involves huge amount of energy. So therefore, it is not affected by external temperature and pressure. Next property, a particular nucleus at one time will either emit an alpha particle or a beta particle, but not both together. Lastly, some nucleides like U235 always decay by alpha decay. Other nucleides like carbon 14 always decay by beta decay. And some nucleides like actinium 227 can either decay by alpha decay or beta decay. So these are the properties of radioactivity. Now let us talk about nuclear radii. How to estimate the radius of a nucleus? Right, nucleus we cannot see, atom we cannot see, so how to estimate the radius? Nuclear radii is estimated by bombarding the nucleus with more than 200 MeV electrons, so that the de Broglie wavelength of the electrons is smaller than the nucleus. So with this, we can estimate the radius of a nucleus. The radius of a nucleus is given by this formula, R equal to R naught, a to the power 1 by 3. R naught is the radius of the hydrogen nuclei, that is 1.2 femtometer. Femtometer is 10 to the power minus 15 meters. Now some books may say that as 1.3 femtometer, some may say 1.1 femtometer. So whatever is given in the question you follow, but average is 1.2 fm. Now based on the mass number, we can find the radius of any nuclei. It depends on the mass number. It does not depend on how much of it is protons, how much is neutrons. You look at the overall mass number and use this formula, R equal to R naught a to the power 1 by 3. Now, this formula is not applicable for halonucleides. Halonucleides are discovered in the late 1980s and they have got too many extra neutrons, like lithium 11. So lithium 11 is having 8 neutrons and only 3 protons. Because of so many neutrons, in the nucleus of this lithium 11, there will be 3 protons and 6 neutrons sitting inside, and 2 neutrons which are still there extra. They form a halo around the nucleus. That's why these are called halonucleides. Halo is something that you see around statues of gods, goddesses. That halo makes it bigger. So remember this, that R equal to R naught a to the power 1 by 3 is not applicable for halonucleides. For all other nucleides, we can apply this formula. If you know the mass number, just use this formula and you will get the radius of the nucleide.